And perhaps you can start with a slow introduction, especially yourself and this really international group of authors. So please.
So thank you very much for the chance to give a talk here. And thank you a lot for changing the slot after the total blackout in Spain. I couldn't give the talk 2 weeks ago. So I'm very happy to talk about this paper we published. So you asked for the authors. The authors are the following: the Alexander Leguizamon Roballo and myself and Max Tchaikovsky. We were working together in Aalborg University in Denmark last year, and Alexander was a PhD student of Max, and he's now a doctor. He got his PhD, and I was a postdoc in a postdoc position with Max in Aalborg, and then we have as collaborators Mirko Tripastone and Andrea Van Dam, both from Italy. The first working in Lucca in the IMT, and Andrea is working in Sant'Anna Scuola in Pisa. And we were working together in this topic about approximate constraint lamping of chemical reaction network, mostly directed in terms of the first part of the title, the approximate constraint lamping. So we've been working together in lamping for a while, and in this joint work, we try to make an extension of the classical model reduction technique called lamping into an approximate version that allows better reductions and approximate solutions for some models in physics and biology and so on, in particular focusing this chemical reaction network, right? So the talk is going to be as follows. I'm going to first introduce what is this model reduction technique, and in particular, I'm going to focus in this lamping, more from a mathematical perspective. And then I'm going to introduce what is this numerical clue, which is the numerical lamping technique. And in particular, the implementation that is behind it, because all I'm going to talk about today is implemented in Python already, and you can just check it out in the website at the end of the talk. You can get the code for yourself. You can run it for any model that fits into the setup of this technique, and you can get your own results and maybe even cite our paper at some point. Why not? So let's start with model reduction. Model reduction is essentially a way that we have a model. In this case, is going to be a differential system of first order, and we want to reduce it in some way, keeping some information. The ideal, if we could, would be to reduce it to an equivalent system. So whenever we have a solution in the reduced system, we have a solution in the bigger system, and so on, and vice versa. But of course, when you reduce too much, at some point you lose some information. So what we are going to focus here is a reduction technique that keeps some part of information. We are going to focus on this point later. But to start with, we are going to consider a first order differential system where we have a set of m variables that are going to be our basic state, and they evolve through time following some rule. And in this case, this rule is noted by a function f on all these variables. Some of you may notice I said these variables evolve in time, and I didn't add the time in the function, but I can add it as a new variable with derivative equal to 1, and then it will be equivalent. So I will focus on this type of autonomous differential systems. And in this case, n, the number of variables, is the dimension of the system, and the goal of this technique that I'm going to present here is to reduce the dimension of the system. If we consider any application of differential equations, at some point we want to simulate, and when you do simulation, the size and the dimension of the system is quite critical to get a fast implementation. So sometimes the systems that we're going to work with here are huge. Huge, I mean in the tens of thousands or even hundreds of thousands of variables. These are some biological models that comes around trying to model how for example, there are some papers that tries to think how a cell works properly. So they have to take into account all the chemical components that are inside, and this leads to huge systems. So simulating this system may be crazy, and maybe we don't care about all the information, but just a part of it. So maybe if we find a smaller system that can allow us to reach this information, this could be good. And this is what we call lumping, essentially, right? So a lumping, in this case, is a matrix that compress our variables into linear combination of the original state, the x's, such that they satisfy their own differential system. So more formally, if we have the system x prime equal f of x, we say that our matrix L that compress from n variables to m variables in this way, the new variables are y, and we say they are equal to this linear combination of the x's. If we compute the derivative of these new variables and they satisfy a new differential system only involving the y, so we forgot about the x's now, we say that this matrix L defines a lumping in the system, okay? So as an example, here we have a small toy example that we are going to work a bit through the talk. Here we have three differential variables, x1, x2, x3, and their derivatives are equal to some polynomials in these three variables, right? The first one is just this degree 2 formula. X2 prime is just this linear combination of x1 and x3, and so on. And we can check quite nicely that this matrix L that we have here, 100012, is actually a lumping of this system, because if we consider these two new variables, the y1 equals x1 and y2 equals to x2 plus 2x3, which is just this matrix multiplication over here, we have that the derivative of y1 is the derivative of x1, and we substitute using the system above, and we realize that, oh, this thing over here is just the square of what I have defined as y2, so I can just write y2 squared. On the other hand, if we take the derivative of y2, that was x2 plus 2x3, we have to compute this derivative, and using normal derivation rules, it's just the sum of these two guys over here with a 2 in the second one, and we can see that x1 will cancel out, and we will get something that involves precisely this formula, minus 2x2 minus 4x3, which is precisely minus 2y2. So here we were able to compute the derivative of the new variables y using only these new variables y. And that's why L is a lumping, okay? Yeah, so formally speaking, we have defined what a lumping is. If we want to look at it as in a more functional way, from a functional perspective, we have here our variable, our state variable x's, and we have our map f that maps to the derivative. So L, a lumping, is just a projection map that goes from higher dimension to a lower dimension that maps x to y, and it will map x prime to y prime, right? If we just look into these two. So essentially, L will be a lumping if we can find out a map, G, here, that makes all these diagram commutative. So you can do F and L or L and G, and you end up in the same place, right? So this is kind of the functional approach, and you can in fact define lumping more generically than just with a matrix, but with any functional L that allows you to do the completion of the diagram. But we are not going to focus on that here. And the idea is kind of your finding. So if you have F and you have an L, it will be a lumping if you can find this G on the other side that essentially allows you to write this commutation rule, right? But this is too analytical for me, at least from my background. I prefer things more algebraic. And if you go to the literature, you will find in a paper in the 80s, almost 90s, by Lee and Rabbit, a characterization of a lumping using the Jacobian matrix of the function f that defines the differential system, the original differential system. Okay? So in this paper, they prove that our matrix L is a lumping if there is another matrix A of x, such that you can have this kind of commutation rule for the Jacobian. So you multiply the Jacobian from the left by L, and it has to be equal to this matrix X, A of X times L, right? So you can move the Jacobian to the left of L, and it changes in some way that it's just this matrix A. And this has to hold for every point in the space, for every X, and you
We don't hear you. Sorry. We lost your sound.
hear me now? I hope so.
No,
sorry.
it's better, much better. Okay, please go back to the theorem of Lee and Rabbits.
Sorry, my headset just disconnected. So, as I was saying, we have this theorem of Lee and Rabbits that allows you to essentially move the Jacobian from the right of L to the left of L in some sense, and this equality has to hold for all x's. And as I was saying, this is equivalent to saying that the L is invariant under the action of this matrix, this Jacobian, right? Good. So as I was saying, I like things algebraic, and moreover, I like things when they are computable. So in the sense that I can code things down and I can program everything, and I have a criteria and a computable criteria that I can check these type of identities, right? And in a paper by Ovchinnikov and collaborators in 2021, they proved that if the F, the dynamical system you had was polynomial, in the sense this right-hand side of the differential system is a polynomial function, then the Jacobian is a polynomial matrix, so all entries in the Jacobian are polynomials, and you can split it into constant matrices times a monomial. And if you do so, and you collect all these J sub T that we have here, it is equivalent for L, for a matrix L to be a lumping, if and only if for all J sub T, there is another matrix A sub T, such that this kind of commutation rule holds. It's the same, let's go back, the same as we have here for all x's, now it holds for all matrices JT that goes with a monomial in the Jacobian matrix. Or, equivalently, is the same as saying that L is invariant under all the J sub T that we are having here in this decomposition. And in fact, they implemented this idea in an algorithm called CLUE. And we will talk about it later, but first of all, let me talk about constraint lumping first, yes? So I've been talking about lumping. Lumping is a matrix, it's a lumping or not from a system. And we can check if it's a lumping by using the previous result. Good, fantastic. But as was shown in this paper by Deming, Demitzaki, and Pogudin in 2024, lumping is not so trivial to construct by itself. There are, at the same time, too many options and too little, in the sense that you can reduce the system, that's true, but you need to kind of say what you want to preserve. Otherwise, you can preserve many things at once. And at the same time, not all systems allows a lumping, right? So usually, when you have a huge system, you want to reduce it. That's one thing. And you want to reduce it keeping some part of the information. And this is what we call the observable. So usually, let's say you have a chemical reaction and you want to focus, you have many reactants and products here and there, they keep reacting and they have, let's say, hundreds of variables, but you only care about the amount of CO2 that is produced at some point in time, for example. So this would be your observable. You want to focus only in the CO2. So you can maybe reduce the system preserving this information, just that information, right? Or at least that information more precisely. So this is an observable. And if we focus on that, it's much easier to define a lumping that holds that information. So we define an observable and linear observable. In this case, you can generalize this theory to non-linear observables too. And we define it with a matrix M that combines the original state variable, x's, and gives you some linear combination of the variables that are the information that you want to preserve in the reduced system. And then we say that a lamping L of the system is constrained by this observable if there is a linear combination of the new variable, y, such that you can recover this information. So essentially is what I'm saying. You want to preserve the observable, so you reduce the system in a way that you can recover this information. And this is what is coded in this equation over here. And if we write everything down just with matrices, we realize that this means that the observables, which is this m times x, is equal to the matrix A, is a matrix A, L, X. So essentially what we are saying is that the observables are in the space generated by the rows of this matrix L, essentially. Okay? This is a very nice and algebraic way of phrasing that the lamping is constrained by some observables. So with this, as I was saying before, Ovchinnikov and collaborators built an algorithm called CLU from the beginning that computes the minimal constraint lamping for a given observable. So you have an input, as an input, the full differential system, and a set of observables, linear observables that you want to preserve. And this algorithm computes the minimal lamping in the sense of dimension that preserves this information. So once you are done with this, you are guaranteed that you get the minimal differential system that you need to represent these observables. Okay? And how is this algorithm working? So you say, okay, I start my observables will be my lamping for now, and then for each matrix in the decomposition of the Jacobian, using this decomposition via monomials that I talked before, we try to make the matrix L that we have invariant under this operation. So we essentially multiply L times the Jacobian part, and for each of these rows we check, is this row in the space spanned by the rows of L? If it is, we do nothing. If it's not, it means we need to add it to our space, and then we keep going. So essentially, if R is not in the space of L, we increase the space by adding this new row, essentially, right? And we keep adding more and more rows until everything is fixed and we found an invariant space under all the Jacobian matrices at once. And then using the result by Ovchinnikov, we have that the L is invariant under the Jacobian, the full Jacobian now. And using the result by Lee and Rabbit, then we have that L is a lamping. And the good thing here is that they prove in this paper that this is precisely a minimal lamping for this, right? So you cannot get any better than what you get from this result over here. So some things that are worth remark here is in this algorithm, there is one part here that we check R is in or is not in the space of L. And this can be done quite nicely with Gaussian elimination. We will focus on that later. And also I want to remark that this algorithm of CLU was extended already by me and Michael and Gleb Pogurin and Jacob, also in 2022, a bit later than this paper by Ovchinnikov. To rational functions. What was the main idea there is that the result that they had for polynomials, you can do it again, but now instead of splitting the Jacobian into constant matrices times monomial, you can split it into constant matrices times some set of functions that are linearly independent. And if you have that linear independence between the functions, linear independence with respect to the rationals, then this decomposition will work and you have the same equivalence as you have in the polynomial case. So in particular, we work it out with rational functions and we implemented that case. But as a remark here, you can do this for any computable representation of functions where you can do this split of the Jacobian of my matrix into a set of constant matrix times a function, and these functions are together a linearly independent set of functions. A bit of many things here. And as I was mentioning, just a final remark, everything is implemented here in this repository of CLU. The CLU algorithm is implemented there, and there are many extensions going around, and it's still being working on and nowadays, and improvements are done more and more. And you can just try any differential system of this kind, polynomial and rational, and you can just give it an observable and try to get the best possible reduction, preserving this guy. However, and this is kind of the motivation of this paper, essentially, CLU and this exact reduction, this lumping,
Again, we lost your voice.
yes, sorry, it just keeps shutting down. I hope now it will work.
Okay, now it is good.
Okay. Is it working?
It's okay now.
Yes. Yeah? Okay. Good. Sorry for the technical issues. So, as I was saying, CLU is very sensitive to the coefficients in the system. What does this mean? Okay, let's take back this system that we have before. In the example, we have 3 variables and we have these coefficients, and we knew before that this matrix L, 1, 0, 0, 0, 1, 2, is a lumping. This means we can, in order to read x1, we don't need 3 variables, we only need 2. And the second variable is just the x2 plus 2x3. This is what this means, essentially. So let's assume for any reason you are building a differential system for your model, and it turns out that you cannot measure exactly one of the coefficients, but it will make a small mistake in one of them. Let's say here, instead of a 4, our measurements are not so precise that we can say it's exactly 4, but it's, yeah, 4.0 something, in this case 4.05. And then we try to run CLU again and see if we can reduce the system, and CLU will tell us, no, you cannot reduce the system with this matrix. And in fact, you cannot reduce the system for reading x1 because there is no such reduction anymore. So here we can see that if you are applying this to an actual setup where the coefficients of your model are not exactly given, prescribed, then it's very possible that when you try to apply the technique, it's not going to work and you are not going to reduce anything. So this was the motivation for what is coming now, that is the numerical CLU. Numerical CLU is what we develop in Aalborg with all my collaborators. Let's recall Alexander, Max, Mirko, and Andrea. And we all worked on this idea that is essentially, yeah, okay, you have your algorithm. And yeah, the main problem where the place where the exactness of the coefficients come into play is the part of the algorithm here, where we need that the vector, the new row that we are checking, is exactly in a space, in the space generated by L. And this is too strict for this. So let's allow some error distance, let's call it epsilon. Whenever we add a new row, we allow this distance to our space. If you are closer to the closer than this distance, then we understand that the vector was already in the space, but we were making some numerical mistake, and we don't add the row. And then if we are far away from the space, then we add the row. So essentially, from the original algorithm, we just change that line over there and say, okay, if the distance is bigger than the error we are allowing, then we add the row. If it's smaller than that, we say, no, it was already in the space. It's a very natural assumption and a very natural thing to do, right? You are making numerical things, and yeah, at some point you have to say something is 0 for me, right? Maybe 10 to the minus 16 is 0 for actual computations, right? So yeah, the thing is there, we have this, and now we have this, instead of having something is in the space, we have the distance is bigger than. So there, as I was saying before, we were using Gaussian elimination to do this check, right? We were checking if something is in the space using Gaussian elimination. We have a basis, we do perform Gaussian elimination on our vector. If we get all zeros, it's in the space, we are done. If you get something that is not zero, then you can add just that vector to the matrix, and it will keep it in a very nice way in the row echelon form. So it's ideal for exact data because you can just do things on the fly, very easy to implement. We know it works, it's efficient, and so on. But with numerical data, as I'm saying here, there are several issues with Gaussian elimination. First of all, if you have numerical noise, the zero recognition becomes a problem because you cannot say if something is actually zero because you may have, as I was saying, 10 to the minus 16, 10 to the minus 9. These numbers are kind of zero, but they are not zero. So what can you do? One, it's a bit tricky. And also another problem that we have is if you apply Gaussian elimination, you have now a vector in a normal form, in this row echelon form, and now you want to measure the distance to a subspace. It's not direct. You need to do more computations to compute the distance. So it seems that Gaussian elimination was not the way to go. So what did we do? Yeah.
Sorry, I have a question, and maybe it is related. How do the results depend on the value of epsilon?
We will come into that later.
Okay,
yes.
thank you.
Thank you for the question. And in fact, that will be kind of the whole thing of experimental results afterwards, right? Because as you were suggesting here, the bigger the error you allow, the different results you will get. And there are many things to study there. And yeah, we will see later that if you allow a big error, then you reduce too much. And if you don't allow any error, you just recover the exact reduction. So that will kind of answer the question very briefly. We will come into more details later. So coming back here, Gaussian elimination, not a good idea. So what can we do? We use orthogonal projections. This is the natural thing to do when you want to measure distance, because you can check if something is in the space by just checking if the orthogonal projection is the vector or not. So you have a vector, you project it down to your space orthogonally, and if the vector remains the same, does not change, then the vector was already in the space. If it changes slightly, then it was outside. And moreover, this difference between the orthogonal projection and your vector, it gives you precisely the distance of your vector, the original vector, to the space. So orthogonal projections look the perfect tool here for computing this algorithm now, the numerical clue. Some technical details here, right? Computing this projection, the orthogonal projections can be done by taking this matrix. So you have your L, your L defines with its rows the space you are projecting into, and then you multiply from the left with the Moore-Penrose pseudo inverse of L, meaning that if you multiply this L times L bar, you get the identity. If you multiply it from the other side, you can also do that. Then you get a square matrix of n times n. That will not be the identity most of the cases. But, and when you have these two products, it will be precisely the orthogonal projection operator. Why we care about this? This is a bit technical, and Moore-Penrose pseudo-inverse may be tricky to compute. So usually you don't want to keep L as it is, but you want to keep it orthonormal, as in the Gram-Schmidt algorithm, because then the pseudo-inverse is just a transpose. And this is very nice and very helpful for computing things, because you just need to transpose in order to get this inverse, right? Good. So with all of this, this is kind of the intuition that I was saying before, right? You have your vector and you have your space, this blue space that is just spanned by the rows of L. You project it down, and this green line, that is the difference between your vector and the projection, is distance between the vector and the space. So it's very easy to just measure this distance that I was saying in the intuition before, in the key idea of numerical clue. with orthogonal projection. And then the algorithm just gets like this. So it's the same idea as before, but with a small technical changes here and there. So before we just started here, our L0 was exactly the M, the observable matrix. Now we compute first the Gram-Schmidt of the vector in the observable matrix, and this is our starting L. And now we do the same. We compute the L times our Jacobian decomposition as we had before. And for each row, we compute the difference between the vector and the orthogonal projection. This is what is going to give me the distance. Then we check if the distance is too big. Then we normalize this new row and we add it to the matrix L, which makes it directly orthonormal. So if I add this R to an orthonormal matrix already, since we know R is orthogonal to this L, that this matrix remains directly orthonormal. So we can just easily update the projector operator and we can just keep going. And we repeat over and over until we stabilize. At some point, we don't add any further row in a go here. And then we know that our matrix is invariant under all the JPs. And as before, if we are invariant under all the matrices in the Jacobian decomposition, it's invariant under the Jacobian. And if it's invariant under the Jacobian, this L is a lumping. So in the previous example here, where we had our coefficient just moved away from 4, just slightly, let us now run clue, this numerical clue with an epsilon of 0.1. Here I show the Jacobian matrix of this system. Let me just go back briefly. The Jacobian of these three functions over here is just the derivative of each of the functions by each of the variables, x1, x2, and x3. And we get this matrix over here. And I just depicted here with colors this Jacobian decomposition that I was mentioning, right? I was taking now the green matrix. It's just the coefficients of the monomial 1 in each of the entries. And we see that the J1 is just a row of zeros because here there is no constant coefficient. And then we have 2, 0, minus 4, and then we have minus 1, 0. And then we have two more monomials appearing in this matrix, x2, x2, and x3. And we just show here the decomposition into the three matrices. Good. So what we need now is to be invariant under these three matrices at the same time. They are very easy matrices because, for example, J2 and J3 have two rows that are full of zeros, which will simplify computation a lot. So we want to observe x1, and x1 is represented by this vector over here. So we run clue starting with it. So in the first go, we multiply R by J1, J2, and J3. We get three vectors. And now we want to see if these three vectors are in the space generated by L, in this case, the 1, 0, 0. So we start with the first one, 0, 0, 0. It's clearly in the space because, I mean, it's the zero vector. This is in every space. So we do nothing and we continue with the next. Now we take this one. This is not in our space because, of course, we cannot generate this vector with 1, 0, 0. So we compute the orthogonal projections and the difference with the original vector, and we get the same because in this case, with this space, the orthogonal projection is just removing the first coordinate, and it was already 0, so nothing to do here. And we check. We take the norm of this guy, and it's clearly bigger than 0.1. We have a 2 and a 4 in the entries. This is bigger than 0.1 for sure. So we normalize this vector and we add it as a new row. So we just take the norm, divide, we get this vector over here, and we add it to our L over here. Fantastic. We move to the next one that we got already. The 0, 4, 0.05, and 8. Now, it's not as simple to compute the orthogonal projections, at least mentally speaking, but a computer can do this no problem. And we check how is the orthogonal projection, the difference between the vector and the orthogonal projection over here, which is essentially this product. And we see we get 0, 0.076, and minus 0.046. Okay, we compute the norm of this guy and we get 0.089, which is smaller than our error, the error that we allowed in this run. So we don't add this vector because it's smaller than the distance that we allow, and we continue, no problem. So now we have checked already the first row multiplied by every of the Jacobian matrices. So now we start with the second row, and we do the same. We multiply by each of the three Jacobian matrices, and we need to check these three cases. So we start with the first one, is this vector over here with three coefficients that are negative. Why not? We compute the orthogonal projection, the difference with the vector, and we get this result over here, 0, minus 0.168, and 0.010. Okay, we check the norm of this guy. It's smaller than 0.1, so we do nothing. We keep moving forward. The 0, as before, is in the space. We do nothing, and the same happened with this last vector. So at this point, we have checked that every row in L can be multiplied by the Jacobian matrices, any of them, and the result will be already in the space. Will be in the sense that the distance from this vector to the space generated by this matrix L is smaller than the epsilon that we prescribe. So we return this matrix L as our numerical lamping of the system that has this small perturbation in one coefficient. And it is very interesting to remark that this lamping matrix, after allowing this small error, is exactly the lamping we had before with exact clue, with the exact coefficient, right? After and before the perturbation, we had a lamping that was the 1,0,0,0,12. And now we obtain this matrix over here, 1,0,0,0, and these two coefficients. And we can check very easily that this one is basically, and if you don't remove, if you don't remove more decimals, you will check that these guys are just related 1 by 2. So this coefficient is the double of this coefficient over here. So kind of when we run numerical clue in a perturbed system, we recovered somehow an exact lamping from the true system that was behind. Of course, there is no guarantee that the true system had any reduction, but it is kind of hinted that this works because of this, right? So some remarks from this numerical clue. For epsilon equal to 0, this algorithm leads to exactly the same algorithm as clue. It will provide the same exact reduction. And as I was saying, if the system had some small numerical errors, it seems that you can recover the true reduction of your system. And it will kind of be hinted that, at least in examples, that if with a very small epsilon, a very small error, you get some reduction, it kind of means that your system was already not exact in that sense. And probably you will need to check a bit that maybe your system is a bit perturbed by some numerical error over there. And then if the system has no exact reduction, that could happen too. Or even if it has an exact reduction, you can even reduce it further by increasing the epsilon. As I was saying before, if you keep increasing the distance that you allow in the numerical clue, then you will discard more vectors on the space, and at some point you will end up with a smaller space than you should. This, as I will show later, will lead to some simulation error. I'm going now to describe what is this. At the expense, so you gain in the sense that you get a smaller system, but then you pay an error in the simulation. It's something you have to deal with at some point. And in fact, whenever you have numerical clue, you will probably have a numerical error so in the simulation. So you need to be very aware of that. And what is this error in the simulation? Well, you need to be precise on the definition. So let me take a solution in the time of the differential system. And then let's take a solution of the reduced system. The reduced system will be precisely the one that is obtained by this formula over here, like y prime is equal to the lumping matrix times f times the pseudo inverse that I was mentioning before. This, if we have an exact lumping, this will be the reduced system. If you don't have an exact lumping, this equality is not correct, right? So there will be a difference between what you get here when you take a solution to the system and do the linear combination and the new variables that you get, right? If this is an exact lumping, it is easy to prove that this difference is always zero. So in the numerical case, this is not the case. This will be different than zero, and we have an error. So how big is this error, right? This is kind of the tricky question. How bad can you make it when you do this numerical lumping, essentially, right? And the answer is that this error will be linear in the epsilon. So the smaller the epsilon, the smaller the error you make. The bigger the epsilon, the bigger the error. And this relation is linear, right? However, this theorem has some tricky points in the statement. So essentially, if you fix a set of initial conditions, so you fix x0, the starting point, and you fix a time horizon t, a capital T, that you are going to look forward, then you have to assume that your true solution is bounded in this time, so you don't explode, which is a reasonable assumption. And you assume that the L is the output of our algorithm with some tolerance epsilon, then there is a constant that depends on the function, the set of initial conditions, the matrix you are computing, and the time horizon that is greater than zero, such that the error is smaller or equal than epsilon. The epsilon we fix times this constant over here for all t's in the time span that you are looking for, right? So this is a nice result in the sense that, yeah, you can make the error as small as you please just by reducing the epsilon. Of course, the smaller the epsilon, the bigger the reduction in sense of dimension. So you will have bigger systems to compute the simulation, so you are not gaining as much time for simulation. But you are reducing the error of the simulation itself. So it's a trade-off here. You need to pay something to get something. If you want a smaller system to check something quickly, then you need to know there may be errors. And if you don't want any errors and you want to be very precise, then you need to essentially do exact lumping and hope for the best. Good. So I'm going to go to the experimental results here that we kind of prove in this, we tried in this paper to apply this technique to chemical reaction networks and some other models, not only from chemical reactions, but also from biology. So these are three models that we are going to look into in this talk. I'm not claiming I understand anything of this paper, and the models they provide, I don't really know where they came from. I know there are models that try to tell me how things interact. So, for example, the first one tries to talk about the carbon pathway of E. coli, converting glucose into something else. Why not? It's a problem that they are worrying about. And the model they have is a differential system of other one in the sense that they measure how much the concentration of something changes through time, and that depends on how much of all the reactants are in the place. So there are three models. As I say, I'm not claiming I really understand the meaning behind them, but I understand the math in them. I understand the differential system, and we try to reduce them looking into observables that they read in their paper. So, for example, in the first paper, they really look into the concentration of this 1,3-diphosphoglycerate, that was called D13PP in their paper, and they look for this particular substance through some specific time. So we in this paper run this numerical clue for this particular observable, and we simulated until that time that was specified in the paper. So we kind of were trying to actually do what they did, and we were measuring there the errors and so on. So summary, big tables, we all love tables. In the first experiment, the one with the Bionet gen with this D13PG, it's a very interesting result because here we see in this column over here the value of the epsilon that we were working with, and here in the first column the size of the reduced model we got when we applied numerical clue with this epsilon over here. So in the first one, the original lamping, the exact lamping was of size 30. And we see if we have a very small epsilon, we don't gain anything. We still have 30 in the reduction. But as we increase the epsilon little by little, the size of the reduced model is decreasing more and more. This is good in some sense because then simulating things is faster, but there is one problem. The error may increase, right? This was kind of the result of the error estimation. And that's precisely written here in this column. This is the relative error we are making. And we can see here we make a lot of error here. Here, when we were still exact in some sense, so here when the epsilon was small, the reduced model was as small as the exact lamping, and then we made no error essentially in the simulation. But as soon as we jump into a small reduction, then the error was quite big, like 30–40%, and at some point it just got huge in size. So there was a huge error here.
Excuse me, Antonio.
Yeah.
I wonder if you had the same 30 variables. So
yes,
numerical method give the same 30 variables.
Very good question in that regard, and the answer is yes, it's the same exact things because essentially if you get the same size, it's because you didn't remove anything. So when you are doing numerical clue, you are picking a row, do I add it or do I not? If you add all of them because you don't discard any of the rows, then it's exactly the same rows as in the exact clue, so you get exactly the same variables. Or equivalent, in the sense like exact clue do it with Gaussian elimination, here you do it with orthogonal projection, but the space they generate is the same. Yes.
Thank you.
Very interesting question. And in fact, we will give more information on that regard later. So in this first example, it's very clear that we are losing a lot of information when we push our lamping forward. It's true we can reduce more, but at the same time you lose too much information. So let me go to the second experiment. This is kind of interesting. The second model had 24 species at the beginning, and when we performed exact lamping, we got 19. Well, it was a small reduction, but well, it is what it is. And when we start with a small epsilon, here, a small error, we get the same exact lamping. Yes, I was saying before, since the smaller the epsilon, the closer you are to the exact lamping, then this is kind of expected. And then when we jump, we increase a little bit. Now, epsilon, we get a small jump in the reduction, a very small, right? We got from 19 species to 18 species, and the error was not that bad. Okay, this is an improvement, but not huge. And then the next jump that we got is if we increase more epsilon, then suddenly we jump to 8 species. 8 variables in the reduced system. And as we can see here in the error, this was already too much. And yeah, we made a huge error here. So yeah, in this case, the exact lamping technique was good enough because it reduced to the kind of the best thing you can do. The best next thing is this 18, but that's not a huge improvement. Well, not the worst thing, but we can see here an improvement where we don't lose many information. Good. And the third experiment is very interesting, and this is one that I want to point some focus. Here, the exact reduction, we started with 62 variables. The exact reduction provides no reduction. It tells us, no, you cannot reduce this. If you want to observe the variable we were looking for, you need the whole system. No, you cannot do anything better. And then we start doing numerical clue, and something weird happens. We try with very, 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 very small epsilons, and in fact, we keep making we reduce epsilon as much as we could until it made already that epsilon was numerical noise and we couldn't recognize anything. And it turns out that for all of them, we get a reduction, a numerical reduction from 62 to 28, which is around half. Half of the system was gone. And when we measured the error in this substance that we were looking for, there was essentially no error. It's 10 to the minus 9. That's negligible, right? You can say even it's numerical noise. So it is very interesting, this system, because we couldn't reduce it exactly, but when we tried numerical clue, suddenly we could reduce it quite a lot, 50%. And we didn't make any error here in the simulation. So this is, in my opinion, of course, there is no proof of this. This is hinting to this system, this model over here has some numerical errors in the coefficients, some small inaccuracies that are not allowing to read the actual model, because having an exact lumping is very tricky. You have to have the exact coefficient. And if you are so close to one lumping as here, like, yeah, you just allow this small error and suddenly you go into a reduction, then it kind of means something. It means that you are probably have a numerical issue in your model. But that's my take. Of course, we have no proof of that, like a mathematical proof. But yeah, we have these three experiments. And as it was asked before, picking the epsilon is very, very important because it will change the output. And yeah, having a good heuristic for picking epsilon is crucial to have a quick find information of your system. Of course, you can try many epsilons and then you compare results. That's good, no problem. But when you have a huge system, you would like, then running this algorithm will take time. So you would like to have one epsilon that gives you some information without losing too much information. And picking this epsilon depends on the model, depends on many things. So it's not that easy anymore, right? We will need to know the constant in the theorem that bounded the error somehow. And that is tricky without actually solving the system. So I would like to point out that this is something that is very easy to prove, that there is a maximal epsilon such that in the first round of the algorithm, when we check the first row, if we pick epsilon as the maximum of all the norm, then we won't pick anything. We won't add anything to the matrix L, so we will just keep the observables. And then this epsilon maximum, when we pick epsilon beyond that, then all the reductions will be the same. They will reduce as much as they can everything to the observables. And that, of course, will lose all the information. So can we pick something that is reasonable between 0 and this epsilon maximum that can be computed? And that's not that difficult. Well, that's tricky. And in fact, here we can see in one of the examples, the first one, that we have several reductions, two graphs. The first one, the one on the left, it moves the epsilon from 0 to the maximum epsilon. This is just a quotient between the two. And we are plotting the size of the lumping, the size of the numerical lumping that we are getting. And we see that it is quite normal that you get jumped. You get kind of a stir. The bigger the epsilon, the smaller the model that you get. And you see here there are several jumps. And here on the right, we have plotted the variable that we were observing depending on these points on the graph. And we see here that the blue line is the exact line. So this is the actual value of the concentration of this species in the model. And we can see that if we have a small epsilon, that we are still here in the exact clue, then the result is exact, good. And as long as we jump down in the stair, we make some numerical error here. And for example, the green one was very good until some point, until time 20. The red one was good until maybe time 10 and so on, right? So it diverts with time, but sometimes, and this is something we are now looking into, you preserve some properties like stability at infinity or something like that. So how to pick a good epsilon? Well, that's a whole open problem that, yeah, we kind of think you can make an heuristic about it, but it's very difficult to actually find a final solution to this problem. As I was saying, the ideal way would be to go to the theorem of the error, find the actual constant that is given there, and then you find the appropriate epsilon, right? Because then you can actually bound the error, but that's kind of solving the system, and you're doing this to not solve the system. So it's a trade-off there that I'm not sure how good the restrict will be. So as a conclusion, finishing now the talk, here we have proposed this approximate lamping that is a very natural step to make something that was an exact algorithm numerical. This allows us to tackle some models that have some numerical problems, some numerical perturbations in their coefficients. And we have tested this algorithm in real case studies, so it's actually working. And for the future, as I was saying, you can extend the algorithm for other vector fields. As I was saying, we have polynomial rational functions. You can change it maybe for exponentials or maybe trigonometric functions, somewhere where you can do this Jacobian splitting, the splitting of the Jacobian matrix that I was mentioning before. But of course, that's not implemented right now. We can keep exploring different heuristics for picking the epsilon. And also one thing that will be great will be to prove something about this perturbed system, because we saw there is something there. We get a perturbed system, we recover the original reduction, but can we prove something? Can we give an actual mathematical result that guarantees something? That's still not done, but we will like to work on that. So with that, I would like to thank you. As I was saying, the code is in GitHub, so you can access it and try the algorithm by yourself if you have any example like that fits here. So thank you for your time.
Thank you, Antonio, for your interest.